Okay, so I'm very happy to introduce our final speaker of the session and our final speaker of the conference, Larry Abbott. And in the spirit of my previous enthusiasm for geographic diversity, I was going to highlight that now we have a representation for beyond North America, also to South America, but I think it's not that Columbia, is it? No, okay, so he's from Columbia University, which is apparently uptown. So anyway, thank you very much for being here, and he'll tell us about Fly AI.
I know in a conference that's this rich and intense that the only thing better than the beginning of the last talk is the end of the last talk. So I will try to get you there. In the spirit of free trade that Greg talked about, tariff-free trade we might call it, between these two fields, I'm actually going to talk about how you can use the Fly olfactory system to do MNIST tasks. And that actually isn't a joke. Okay, so, what if you have to do a task like this? Remember the fourth number. Okay, I told you a little bit late, but if you're good, it was a 6, okay? So those are tasks that actually are not so easy for machine learning things, maybe this one, but remembering things across time, figuring out what you should remember, I told you there what to remember, are not the easiest tasks. And so I want to talk about those kind of tasks. You've heard a lot about the machine learning solution for these kinds of tasks, which are this LSTM. In fact, at the first talk of this meeting, David Heeger introduced these, and they've come up many times. So if I can apologize for the advanced math, basically what these guys do is the following. They're like boxes. And if you have some data out there, like a 6 that you were supposed to remember, you can get these things to kind of open a door by internal control, pop the 6 into the box, close the door, and basically keep it around as long as you want, or as long as the system decides that it wants, and then later open the door, pop the memory back out, which is basically what you just did if you had to remember the 6 was the fourth number in the sequence. So it's a very direct solution of a problem of storing things for a while and seeing if you can get it back later. There are all sorts of tricky things here. How do you know what to store? How do you know when to pull it back? But that's the basic idea. And as you've heard many times, these things work pretty well. Okay, but what about, from the neuroscience side, we generally often associate memory with synaptic plasticity. Now here, I want to make a distinction that's very important between learning and memory, and I will try to use those words differentially, but I'll probably forget. Obviously, in machine learning, the learning takes place through what we would call synaptic plasticity. You change the connections between the units in the system, and eventually it's supposed to work. But in machine learning, once you've done that, you freeze the thing and you send it out into the world to do what it does, and those connections do not change again. So instead, if you need a temporary memory or more like just a memory that's part of the task, you use things like LSTMs and do not use synaptic memory. And there's a very good reason for that. So, we focus in neuroscience on things like Hebbian learning. In this case, we might want to think about something like a gated Hebbian learning so that you have a chance to decide when you're going to remember something and like that. That's kind of the going thing. We all believe that memories are stored in some sort of system like this. Now, the machine learners are not going to like that. They're not going to get excited about this idea. And the reason is just numerics. If you have n units at one level of a network and m units at the other, then you have m times n synapses typically if it's fully connected. And that means that whatever computations you're going to do in getting these synapses to be dynamic entities that can change, that can last for a while, change again, you're going to have to do a huge amount of computation to do that. And so actually, despite the fact that this is the leading neuroscience candidate for memory, I think it has almost never been tried in any kind of complex network for this problem, the fact that it's extremely tedious numerically. And in fact, I would go to say that there's a kind of a sadness here, that it's very likely that indeed this is what happens inside our brains. And unless we get better at being able to compute the dynamics of many synapses, we may never be able to do this. This is an extremely computationally intense problem, and I'm going to skip it just like everybody else does, but I have something to propose. So what happens instead, if you've seen synaptic plasticity in a network of any size, for example, Misha Sadek's work, Wolfgang Maaß's work, it's a one-sided synaptic plasticity. It's typically presynaptic only plasticity, which is functionally equivalent to neuronal adaptation. So the reason you want to do this is because now you only have to do n computations. In other words, all of the synapses coming out of one of these units do the same thing now. And so you only have to calculate once per neuron rather than once per synapse. And so essentially all we know about neuroplasticity in big networks comes from this sort of presynaptic only mechanism. I'm not going to propose a solution to that problem. The plasticity I'm going to talk about is also presynaptic only, but I have a trick. The fly has a trick up its sleeve, if flies have sleeves. Okay, so one thing we know is if you're going to do these memory type tasks, so you'll train up a network and then have it do some task that involves storing things away for a while, pulling them out later, you pretty much need two things. One, you need multi-time scale plasticity. It's very hard to do things by saying, I'm going to store it, it's going to last for 3 seconds and go away, because 3 seconds might not be enough, or 3 seconds might be too long. So LSTMs solve this, as you saw in my little diagram. You can open and close the door whenever you want, and you can leave the number in the box for 3 weeks if you choose to do that. And controllable, of course, is that we just don't run a tape and store every fact that comes our way. If we did, we'd have trouble finding the relevance ones. We have to be able to push into memory and pull out of memory in a very controlled way. And in fact, LSTMs solve these together. Because they're controllable, they're allowed to do multi-time scale stuff. Okay, so I want to do the translation. Now, what you've heard already is, of course, about LSTMs, is sort of an attempt. David Heeger did this. Upi talked a little bit about this. And there's a paper from Tim Vogel's group recently about this, is how do you get LSTMs into neuroscience? And you've heard about that. But I want to try going the other way. I want to say, is there an idea in neuroscience that maybe could do the role of the LSTMs, but is different? And to do that, I'm going to go to a system where we probably know as much about memory and how it's controlled and formed as any other, which is the fly mushroom body, and I'll tell you about that in a second. Now, in fact, you'll see my arrow really goes two ways, but that's the idea. Let's propose an alternative that we know exists in biology and see what we can do with it. Okay, so the fly mushroom body. Fly mushroom body is involved in olfaction, so I'm going to take you a little tour through the olfactory system of the fly. The fly smells with these appendages here, these fuzzy things, that act as the olfactory receptors. In those appendages are olfactory receptor neurons. Those neurons express one of 50 receptor molecules that bind to different odorants. They express one and only one, and in that regard, they're very much like your olfactory receptor neurons, although they're built quite differently. Now, from these appendages, axons come into the brain of the fly, and synapse all together. So all of the olfactory receptor neurons that express a particular receptor type will converge within an object called the antennal lobe on a glomerulus and deliver their message there. Again, in your olfactory bulb, a very simple, similar architecture exists. And so this antennal lobe is a relay station. All of the channel of this particular receptor type that's been marked in green here, converge here, and at that point, another neuron called a projection neuron picks up the signal and takes it into, whoops, the rest of the brain. Let me, so the projection neuron comes along and takes it up into two areas of the brain here. This is the mushroom body, and this is the lateral horn, which is responsible for innate olfactory behaviors, and we won't talk about it. The mushroom body, which I'll show you now, is responsible for learned olfactory behaviors, and so it's a memory system. And these cells that you're seeing in red are called Kenyan cells, and the Kenyan cells make the mushroom body. The mushroom body is made of Kenyan cells. So that's the general scheme. From the receptors, relay, up to the mushroom body, and then, well, we have to go on, but we've gotten it to the mushroom body at least. All right, so here's a picture of the mushroom body by itself. Here's a projection neuron. It's coming up. It's delivering its message here to the Kenyan cells, and then, as I said, these green Kenyan cells form the mushroom body, which is this L-shaped, and this is the mushroom part. Object. Okay, so I already mentioned there are 50 basic olfactory channels in the fly. That means there are 50 types of projection neurons. So 50 channels, you're only seeing one here, of information come here. And that 50-dimensional representation of odor space, if you want, gets expanded out to about 2,000 Kenyan cells that respond here. Now, of course, this isn't going anywhere, right? Kenyan cells do not leave the mushroom body, so we better have a next stage to get a message out here, and that next stage is called a mushroom body output neuron. Here's one of them, so it's carrying the signal out to some other part of the brain that will react to whatever the fly has memorized about odors. And there are about 16 channels here. Now, those channels form in compartments. You'll see it better on the next slide, but different regions of these parallel axon fiber structures, the lobes of the mushroom body, is divided into regions, and you're seeing one of those regions here and one of the mushroom body output neurons. But there's 16. So 50 channels come in, get expanded to 2,000, and get crunched down to 16 channels. Now, for every compartment, there is a separate dopamine innervation, and that's the gate. That is going to be the plasticity gate. Plasticity between the Kenyan cells and the output neurons is governed by these dopamine neurons. And I'll tell you in more detail how. Okay, here's a nice slide where you can see the compartments, and this is work from Janelia, from Yoshiaso and Jerry Rubin primarily, who really laid out the whole output structure of the mushroom body in a very beautiful way with beautiful pictures. Here what you're seeing is 5 of the 16 compartments because the different output neurons have been labeled in different colors. So there's 1, 2, 3, 4, 5 of the 16. And so those are different output channels, and here very nicely their corresponding dopamine neurons that innervate them have been labeled, and you can see this nice one-to-one correspondence. This dopamine neuron is responsible for this compartment, this one for this one. So the output neurons and dopamine neurons fall in this very nice compartmental structure. Okay, so I'm going to just tell you a bunch of facts about the mushroom body that without any demonstration or whatever, so I can get moving on. And it starts off with these connections. This is a part called the calyx, where these projection neurons come, deliver their message to the Kenyan cells of the mushroom body. The first thing is that these connections appear to be random, which is very unusual for the fly. A fly is a fairly hardwired device, but not here. And so there's quite a bit of evidence now that those connections are random. That's actually not a big part of my talk, but it's a kind of an interesting fact. The other thing is that both the activity in the Kenyan cells and the number of connections in this calyx are sparse. And I think we have a pretty good understanding from papers from Babadi and Sampolinsky, and in my group from Ashok Lidran Kumar and Evan Schaefer, also work in Stefanos Fuzi's group. I think we have a pretty good understanding that this whole structure is made to give you a very diverse representation of odor space, essentially as diverse as possible, from which these output neurons can pluck off various associations that they learn over time in a sort of unbiased way. The other thing that you, since I'm doing a machine learning kind of connection, there's a global inhibition that comes into the mushroom body, and there's a paper in Science that kind of made a big deal of that with respect to the machine learning thing. And again, I'm not going to talk about that aspect, because really I'm going to talk about the output side of the mushroom body, not the input side. What I just described as the inputs. And the output side, whoops, if I go the right direction, sorry. The output size is, I already mentioned, the fact that it's compartmentalized. So there are different compartments. And in each compartment, I'll give you a little bit more detail on this in a second. In each compartment, the plasticity of the connection between the Kenyan cell and this output neuron is driven by dopamine. In fact, dopamine causes a depression of the connection. So the plasticity here is going to be backwards to maybe what you might naively think. When plasticity occurs, it turns the synapse off, essentially. The last thing is that it is known that there's multiple time scales of plasticity. In other words, different compartments are associated with plasticity that can be easier to induce or more difficult to induce, and will last either a shorter amount of time or a longer amount of time. So this system accomplishes the multi-time scale of memory by putting different time scales into different compartments. And that's going to be a trick we're going to use when we get to machine learning applications. Okay, I just kind of like to draw this diagram. This is a schematic of what the mushroom body looks like. Environment sends in odors through RNs. You get projection neurons, Kenyan cells. There's learning on this connection to the output neurons. I keep pushing the wrong button on this thing, which I didn't think was hooked up. The dopamine neurons, which are also driven by the environment, do this. The reason I did this, some of you may recognize, this is actually a diagram from Frank Rosenblatt's first paper on what he called the perceptron. I just stole the diagram. It's the same layout as he used. Okay, so what am I doing here? Oh yeah. I want to start talking about this in sort of a schematic way, and so I'm going to represent that diagram like this, okay? Output neuron gets input from a bunch of Kenyan cells, and the dopamine is modulating it, okay? And then I'm going to walk you through, and I'm going to walk you through the plasticity as kind of I learned it from work by Daisuke Hattori in Richard Axel's lab on one of the compartments that essentially does the fly's version of what Nicole Russ talked about earlier today, of familiarity memory. So familiarity memory is imprinted on one of these compartments by the kind of plasticity I'm going to talk about. But in fact, many people have worked out the basic plasticity mechanisms that I'm about to schematically show you. Without data, you just got to believe me. So here's how plasticity works in the mushroom body, and we're going to steal this and we're going to stick it into machine learning. Okay, the idea would be the following. There's the basic diagram. Suppose an odor comes along, and that odor just happens to activate these two Kenyan cells that have now shifted to white. So those are now active. They have nice, strong synapses here. That's what I've depicted with these big triangles. And as a result, they will activate this output neuron. And if I'm thinking about sort of aversive possibilities, and that you'll see that's where I'm going, you could think of that as a safe signal. This odor is safe. I have not learned anything particularly offensive about this odor. It's fine. However, if you were to present this odor and follow it by a shock, what you would do is to activate the dopamine neuron. And the consequence of that is, as I said before, is to weaken these synapses. So let me just draw that for you. So here are the weakened synapses. So the idea is activity in the Kenyan cells accompanied by activity in the dopamine neuron leads to weaker synapses. And the consequence of that is that later, if the odor A comes back again, now these weakened synapses will not be strong enough to activate the output neuron, and that silence is a danger signal to the fly. It's countered by another activity in other neurons, and that's the bad news signal. In the past, I've associated this odor with something bad. Maybe I should get out of here. Okay, now, if you have a situation like that where you have memorized an association with odor A, what happens if an odor B comes along? So in that case, again, you'll activate the output neuron. That's a neutral odor. But what happens if you again shock the fly? Obviously, what will happen is you will now weaken the synapses of odor B, just like you did before. That's what I already showed you. And we're going to represent that as the weight of those synapses being pushed to 0. But something else happens as well, which you probably could have figured out what has to happen. And that is that the A synapses get a little bit stronger. You start, in other words, to erase the previous memory. If you didn't do that, this system would saturate after, a number of odors. And you can represent that this way, that there is a resting, if you want, strength of the synapse. That's where I started. And when the dopamine comes in, but the Kenyan cell is not active, you start recovering back to that baseline. And this alpha is the amount of the recovery that happens. So these are the rules that I'm going to implement now in a machine learning type context. Okay, so let me build it up, and then I'm going to tell you more of the rationale. So here's the idea. You have a stimulus. It comes into 2 layers, and now you can think of this as the fly or machine learning. I don't care. I'm going to use it as machine learning. This would be like the antennal lobe. This would be the Kenyan cells here, N Kenyan cells. That's going to be about 2,000. And then you have this parallel fiber system, and now you have compartments. So far, if I just did this, let me go do machine learning language, you'd stick in some stimulus, you process it through layers, and nothing's any different. But now we're doing something kind of funky. And that is we're splitting the output of each one of these N units, I've only shown you 3 of them, into, I've chosen 4 compartments for this diagram, and actually for the examples I've shown. And those outputs are all going to be connected to the ultimate output, the readout units that's going to tell the answer. So this is the M bonds that are going to tell you the answer to your problem, okay? Now, each of these blue compartments implements this rule. If the activity is bigger than some threshold, you set the synapse to 0. And otherwise, if the activity is not greater than threshold, you start to recover the synapse. That's the learning rule. And the key is that these compartments, like in the fly, are going to be associated with different levels of threshold. This is a compartment that's really easy to change. This is a compartment that's hard to change. And also with lifetimes. So this is a very short-lived memory compartment. This is a very long-lived memory compartment. All right? Now, this whole thing, okay, let me just say why this is good. Sorry, I put this so low, you probably can't read it. The key to this thing is it gives you multiple time scales of plasticity, but the number of calculations here is only the number of units times the number of compartments. So it only costs you a factor of 4 here to do a multi-scale kind of plasticity, unlike the Hebbian case, which would have cost you n times m, and m could potentially be very large. It's not from the fly, but it could be very large. So this is a nice compromise to get multiple time scales into the same units without costing you more synapses, more units and more computation. Finally, this whole thing is going to be controlled by a plasticity control thing. That's the dopamine neuron. And that dopamine neuron is also going to get sensory input, so it can decide, okay, I'm going to lay this down in memory. It can even differentially lay it down in one compartment or another. And so that's it. That's the basic thing. Now, this model, I can build this of the fly mushroom body, and I face a problem that I think machine learning gets us out of. And that the problem is that I don't actually know what the fly mushroom body does in nature. Obviously, it makes associations with memories, but doing something like just shocking this model and having it learn that that's a bad odor, that's a trivial problem. It doesn't test the thing. And so I want something challenging for this thing, and given that I don't know exactly what the fly does with it, I'm going to go to machine learning, and where they have tons of challenging problems. And so that's why what I'm going to do here is I'm going to train this up to do MNIST tasks. Before they do that, I have to say one more thing. So there's this difference between memory and learning in this case. This business with the plasticity control, changing synapse, that's going to go on all the time after it's trained. Training consists, in this case, I mean, there are all sorts of connections here, but the relevant ones are these W stars. That's the connection from here to here. And that's what's going to be trained during the training period, and that's what's going to be frozen. So each of these synapses in the compartment has a fixed baseline level, but it's constantly going up and down from that. But anyway, that's the learned parameter as opposed to the memory parameter. The memory parameter is the W. Okay, so I'm going to have this do MNIST tasks. A trivial change. I just, instead of putting an order, I'm going to put in a standard MNIST type number. This layer is a little bigger because you've got to deal with all the pixels, but otherwise the whole thing's exactly the same. I'm going to do the following task. Here's the task. I'll show you the numbers. I'm going to show you a sequence of numbers. It has to be a memory task, right? And at this point, you have to tell me what that number is. That's the classic MNIST thing. It's a 5. But you also have to give me the 5 previous numbers. Okay? Not so easy, especially I didn't tell you what to do, but it wouldn't have been that easy anyway. So you have to give me the 5 previous numbers along with the current one, and then it'll just keep going. So I'll give you another number. Now you have to give me the 3, but you also have to give me the previous 5. You have to shift the previous 5, etc. Give you 9 like that. That's the task to do, and the system works like this. So again, you're going to just sequentially give it the numbers like that. And now we got to build the output units. And if any of you done the MNIST type task, I think you know how this goes. Let's just do the regular MNIST. What you do is from whatever your system is, now normally you would just directly go from here to here. You wouldn't have this funny business. That's where the fly has gotten us something. But you just put what's called a soft max in here, and the number 7 unit goes off, and it tells you a 7. That's just MNIST. That's easy. What I'm doing differently is I've shown this series of numbers. I'm going to have 5 additional softmax units. They're going to read out from exactly the same compartments here, but with different W stars. And they are supposed to tell me then what the previous 5 numbers were. That's the task, okay? A simple task. And let me see where I'm going. Oh, okay. So what was I worried about when I did this in my innocence, I must say? One of the things I was worried about is the following. The 7 has to be determined despite the fact that the synapses here are changing all the time, right? Namely, this sequence of numbers might have happened at one time, but another time a 7 might have come up being preceded by that sequence of numbers. Now these synapses are all different, and you still got to recognize the 7. That's the interference problem that I think Nicole mentioned. And that was in my innocence, because I think anybody who knows machine learning would say it's not a problem. And indeed, it's not a problem. It makes, you don't take any kind of a hit at all for having changeable synapses in here as far as the direct recognition of the digit. Works fine. Okay, there's another problem, and that is that these numbers are being recognized solely by the input of the 7, right? This is not a recurrent network. It has some memory, but the only thing driving activity here is the 7. Okay, so the 7 comes through, and the system has got to recognize that that's a 7, but it's a 7 that was preceded by 35974. There's something funny about that 7, and that suggests it. And it has to be able to do exactly the same if it happened to have been an 8. So if an 8 is driving the network, it still has to recognize those. So these are actually the kinds of things that these networks are very good at. So that's also not a problem. The other thing that you might worry about is time stamping. So these synapses have recorded, if you want, the 35974, but they're all jumbled up. They're all just sitting on top of each other, and somehow this unit has to recognize that the 1, 2, 3, 4th back was a 7, just by, and that's where the multi-time scale plasticity comes in, by just sort of comparing and saying that, well, that one seems the next oldest, to next from the oldest. Anyway, I can't remember what I was going to do here. Oh, yeah. So just to give you an idea, how is this working? Of course, the representation it's using is not the pixels. It's the one in that second layer. But just roughly how it's doing it is following. You can all tell that's a 7. And if you're good, you might be able to tell that that's an 8 superimposed on a 7. That's really what it's doing. It's blocked out these synapses. You can still recognize the 7, and maybe you can recognize an 8. But remember, it's got 5 of those on top of each other. In fact, it's got an infinite number on top of each other. It's just it forgets them. OK, so how does it do? It does pretty well. Here, recognition, as I said, this 0 means that's the current number. It's at 98%, which is as good as I do. It's not world record, but it's good enough. Then, you know, the previous 2 are also at very high levels. Then it falls off a little bit. It's at about 50% in the third. But even when you go 5 back, you know, it's above chance. Am I? Wow, that was fast. OK, I'm really almost done. OK, just let me do one thing. So the plasticity control that I did so far was just to do every single number. But I'm going to do a task now. I'll skip this. I'll just tell you what it is, where we're only going to remember even numbers. So that's easy in this system. You just have to have the plasticity unit only recognize even numbers and trigger on the even numbers. And here's the performance for even numbers. So it's also very good. So the idea here is twofold. One is we can now probe, you know, what is this system capable of doing, even if we're doing funny little business. And the other is I'm just kind of curious how well this would work in machine learning context. I should mention that the way I described it, it doesn't sound differentiable, but it actually has a soft threshold, and everything's soft, so you can differentiate it. These should really be individually controlled units. And you know, I would be able to answer this, except the problem is that the person in my lab, in my group, who's working on this is this old guy who always just complains that he's got other things he has to do all the time. And so I don't have the answer yet. But I hope to one day, and I hope to do more difficult tasks. Okay, I'll end there.
Thank you very much. Beautiful talk.
So this is great, but Jeff Hinton invented this a while ago. And
I knew. I should have known that.
There's a paper about 2 years ago. Just look for fast weights, Jeff Hinton.
Mm-hmm.
And it's pretty much the same formula. So you
Is it multiple compartments?
No.
Yeah,
but the idea that the weights have sort of a long-term value, and then oscillations that can be triggered by, some kind of mechanisms.
Yeah, around, yeah.
In your case, it's different, but the idea is you have these 2 time scales. And the slow time scale is for the like long-term learning, and the fast time scale is really a short-term memory, which is exactly what they're doing.
Yeah.
It might be a little bit trivial, but also irrelevant to your topic directly. But since this model is for the fly olfactory system, do you think it's possible for this model to predict some way that we can make flies like run away out of our houses without hurting them?
Yeah. Well, I can tell you that if you could get channel reductions in all those flies, and you could shine the right light on them, you can train them to fear things just by activating the dopamine neurons. You don't have to do anything. So, you can shine a light on a fly and make it afraid of an odor. So, it's almost solved.
So Larry, the fly mushroom body is actually cleverer than you said, because it's got both appetitive and aversive compartments with separate dopamine modulation of each. Mm. If you built that into your network, would that give you, say, the automatic plasticity control that you show here and allow it to do more sophisticated tasks?
Exactly. So that's the idea, that you need individual control of these with different selectivities. This is what the old guy's got to do sometimes, but that's right.
There's another question, yeah.
So in your network, you have like 4 memory units, and you were able to predict like 3 digits really good, and then your performance dropped. So what if you use like 6 memory units? Maybe you will be able to predict all 6 really good.
I don't, adding memories, I tried a little of that. It does not help a whole lot. unless you get better controlled here. So if you just control them all from one, it didn't work. But I think with individual control, hopefully it works. It obviously doesn't, it's not a spectacular result. One thing I think in neuroscience, if you're a neuroscience want to do machine learning, you can't get into the trap of trying to get as good performance as those guys. You're going to lose that anyway. And, again, it's an exploration of what sorts of things can this do, not necessarily to push it to the limit.
Is there a question in the back?
No, I think that false
Okay.
alarm.
Okay, false alarm. Okay, great. Well, thank you again for that beautiful talk.